All right, so this is the first lesson in the proportion and similarity unit. In fact, I'm not going to have similarity transformations in this notes. I just forgot to delete that from the title. So this is just on ratios and proportions, which is the building block for similarity, which leads us into trigonometry. All right, so if you were here in class, we've already got these notes filled out. If you're absent, this is what we did in class, and you can get caught up. So we say, first, what's a ratio? We say a ratio is a comparison of two quantities with division. By the way, if you were absent in class, we did do a few things on the whiteboard before all this. So there's maybe a few things you're going to miss, but you'll get most of it from these notes. You can write the ratio of A to B as A to B this way, or you can write it as a fraction. And if you have the ratio, for example, of 1 to 4, it means you have 1 part to 4 parts. And the one thing I just want you to be aware of is 1 part to 4 parts means there's a total of 5 parts. All right, 1 here, 4 there, a total of 5. And so one thing I mentioned in class is that this is kind of like odds, like a probability and odds, like an odds in favor of winning would be, let's say, 1 to 4. That means, let's say one person's betting for you, 4 people are betting against you. So your odds in favor of winning are 1 to 4. However, the probability of winning is 1 out of 5, because there's 5 total parts. Anyway, just be aware, 1 to 4 means 1 part to 4 parts, total of 5. Okay, we got to just be careful with units, because ratios are always dealing with often 2 different quantities. But for example, 1 liter to 2 milliliters, we can have 1,000 milliliters to 2 milliliters. And then we reduce it. 500 milliliters to 1 milliliter. Okay, so one place you'll see ratios show up in geometry is examples like this, where we say the ratio of 2 complementary angles is 1 to 2. Find the measure of each angle. Well, one thing to remember is that complementary angles are angles that add up to 90, or 2 angles that add up to 90. In this case, they're in the ratio of 1 to 2. So think back to this. 1 to 2 means there's a total of 3 parts. So if we take our 90-degree angle and just divide it into 3 parts just to give ourselves a visual, that means we've got 2 parts to 1 part. Okay, so it's 2 to 1. But clearly the angles aren't 1 degree and 2 degrees. There's some multiple of that. They've been scaled up by a factor, and that's what we don't know. But we do know that they add up to 90. So we say 1x plus 2x equals 90. So 3x is equal to 90. X is equal to 30. Okay, 30 is just the value of x, and we substitute it back in, and we get this angle is 30 degrees, while this angle is double that, 60 degrees. They're in the ratio of 2 to 1. All right, so pause the video for a moment. Find the 2 angles that have a ratio of 4 to 1 that are supplementary. All right, so next we'll do this problem here where it says the ratio of the angles of a triangle are 2 to 3 to 7. That's just an extended ratio. Ratios don't always just have 2 quantities. You can compare more than 2. So we can draw a diagram, and we say that the angles are 2 to 3 to 7. And again, they're not 2 degrees, 3 degrees, 7 degrees. There's some multiple of that, and we've scaled all these up by the same scale factor. All right, so that means they're in the ratio of 2x to 3x to 7x. That's the ratio. And since they're the angles of a triangle, we know that all those add up to 180. Okay, divide both sides by 12, and you get 15. Okay, so that means our first angle, the smallest angle, 2x, is 30 degrees. I'm just writing it in our extended ratio here. So it's 30 degrees to 3x, which is 45 degrees, to 7x, which is 105 degrees. So those are the 3 angles in the triangle that have that ratio of 2 to 3 to 7. Okay. Well, proportions are just two ratios that are equal. So we're dealing with an equation this time, saying that two ratios are equal. So we're just comparing ratio A to B to the ratio C to D. Now in class I talked about where the names extremes and means come from. I won't do that in the video, but if you're interested I can explain. It's kind of interesting why we have these names for this diagram. But in a proportion, we're going to say that these two values, the A and the D, are called the extremes, while the B and the C, the numbers that are in these positions, are called the means. And again, the names don't really reflect this type of problem in a proportion. They come from somewhere else, but again, I can explain it later. Now, in order for a cross product, or in order for a proportion to be true, the two ratios have to be equal. So, for example, you might have 3/4, and that's equal to 6/8. Now, one thing, if you haven't really noticed before in a proportion, that the means, the product of the means, is the same as the product of the extremes. 4 times 6 is 24. 3 times 8 is 24. So if you have a true proportion, then the cross products are equal. So the product of the extremes is equal to the product of the means. So if A over B is equal to C over D, and we know it's true because it says it's true. We're saying those two are equal. So we have a true proportion here. If this is true, then it's also true that A times D is equal to B times C. And then we just use that fact to solve equations that are written in the format of a proportion. And so we say the product of the extremes, 2 times 7, that's equal to the product of the means, 5 times 3x. So 14 is equal to 15x. Divide both sides by 15. And x is 14/15. Same thing here. Our extremes, the product of the extremes is 3 times x plus 3. The product of the means is 2 times 2x minus 1. In this case, we got to distribute. So we get 3x plus 9 is equal to 4x minus 2. So now we need to do a little balancing. Take away the 3x on both sides. Add 2 over. You get the x by itself. And we get that x is equal to 11. All right, so there's two problems here on the next page that I'd like you to do. You're just going to multiply the products in the extremes, set them equal to each other, and solve. All right, so next we're going to talk about equivalent proportions. In class, I mentioned that, or at least I gave an example of something like this, where I said, suppose 10 and 6 are your means. What are possible values here for the extremes? Well, if you recall, the product of these two should be the same as the product of those two. So 10 and 6 make 60. So you come up with any other two values that make 60. You know, maybe it's 4 and 15. Or 1 and 60, or 2 and 30. Well, 4 times 15 is 60, 6 times 10 is 60. We could have just as well, like I said, let's say had 10 is equal to, or we had 2 and 30, right? 10 times 6 is 60, 2 times 30 is 60. The idea is these are equivalent proportions because their cross products are equal. Meaning the cross products of these are 60 and the cross products of this proportion is 60. So these proportions are equivalent because they have the same cross products. Now this statement here, I didn't really write out how I meant it to say, so we'll cross that out. We'll just say equivalent proportions have equal cross products. Okay, so if you're going to write a proportion that's equivalent to this, the only requirement is that it has the same cross products as the original. AD is equal to BC. So any proportion that has the same cross products is equivalent to this one. And notice we went from A down to B and C down to D. Well, we can go across and compare A to C and B to D. And we know that's true because the cross products are the same as the original, AD, BC. Okay, so these two proportions are equivalent. If you have to come up with another equivalent form, it might be, well, if we can go across, can we go diagonal? Can we compare, you don't need to write this, but can we compare A to D and say that's equal to C to B? You know, is that an equivalent proportion? Well, is this cross product, or are these cross products the same as the original? Well, that's AB. We don't have an AB here. So we can't compare diagonally. That's not an equivalent proportion. But what we can do is just take the reciprocal. Instead of A over B, we can have B over A. And so we have D over C. That's an equivalent cross product, or equivalent proportion. And we can take the reciprocal of the other one we wrote. So C over A is equal to D over B. Okay, so this example is supposed to have a diagram over here. We can complete it without the diagram, but it gave a little context. But what ratio completes the equivalent proportion? So x is to y as, well, x is to 6 as y is to 7. X is to y as 6 is to 7. We know that's true because here our cross product is 7x, here our cross product is 7x. Okay, so write an equivalent proportion to the original. 6 to x is what to what? And then this last one here, y plus 7 is to 7, as x plus 6 is to 6. The diagram would have helped with that one, but we can still write the answer without it. Okay, and then in this problem, it says verify, or at least I want you to verify that this proportion is equivalent to this one. All you have to do is show that the cross products of this one are the same as the cross products of this one. Right? So just show the work, showing that they're the same, and that way you know they're equivalent. All right, we actually didn't get to this in class. Okay, so we didn't get to these last two pages. But I can fill it out here. It says, what would be the best or most specific name for the shape that has the following ratios for its sides? So 3 to 4 to 3. We obviously have to be talking about a triangle with two sides that are the same. You know, maybe it's 3x, 4x, 3x, right? It doesn't mean the sides are 3, 4, and 3, but the ratio is 3 to 4 to 3. But clearly, if the two sides are the same, we know we have to be dealing with an isosceles triangle. Okay, and then in this case, 3 to 3 to 5 to 5, well, it's got to be a quadrilateral. So 3x, 3x, 5x, 5x. I'm only putting the x there because the side isn't a length of 3, it's just some multiple of 3. Okay, and then you say, well, what kind of quadrilateral has two sides the same and then another two sides the same? And of course, you know this one. We've got a kite. All right, so take a moment. What kind of shape would these be that would have this extended ratio? And then I'll come over here and do this very last one. This time we're talking about angles instead of sides. So if you have angles that are in the relationship of 3 to 4 to 3, or 3x to 3x to 4x, well, we also know that if these two base angles are the same, we've got to be dealing with an isosceles triangle again. Now, again, a quadrilateral, and I'm just going to draw a quadrilateral. Okay, it's not to scale. I'm just drawing a four-sided polygon, and we've got 2x, 2x, 7x, 7x. Now, what kind of? It's clearly not a parallelogram, so this diagram isn't the best, but it's just something to get us started. What kind of quadrilateral would have two congruent angles at the top and two congruent angles at the bottom? Well, once you know, kind of think of this as top and bottom, as opposed to this being the top. Think about this. Two congruent angles at the top, two congruent angles at the bottom. So in this case, we would be talking about an isosceles trapezoid. All right, so you've got these questions here to do. What shape are we talking about if this is the extended ratio of their angles? And what shape are we talking about if this is the extended ratio of their sides? Nope, switch that. These are angles, these are sides. All right, so that's it. Finish these notes, and if you have any questions, let me know.